I'd like to talk to you now about the crystalline structure of common engineering alloys. So the main engineering alloys that are used in nuclear reactors are austenitic alloys, which are stainless steel, and nickel alloys. And this is the crystal structure representing those alloys, which is a face-centered cubic structure. And the other main alloys used in nuclear reactors or power reactors, and for sure, are zirconium alloys, which have a hexagonal closed packed structure. And in addition to zirconium alloys, there is also titanium alloys and hafnium. So most of the alloys used in reactor cores have crystal structures that can either be described as face-centered cubic or hexagonal closed packed. HCP, FCC. Alloys with FCC structures, as I said, are austenitic alloys and nickel alloys, and those with HCP structures are zirconium alloys. The other common engineering alloy type are the body-centered cubic alloys. Now, but these are not used within the cores because they become brittle. Certainly, they exhibit low temperature brittlement, and they're embrittled by low doses of irradiation. So, although they are used at the exterior of the core and in the balancer plant, either for the pressure vessels or pressure vessel piping, in regions where the radiation damage, the neutron flux is very low, and so that they don't degrade quite as in a very rapidly, and it takes a long time before they exhibit degrees of embrittlement which would make them unsuitable for further use. So you probably heard about pressure vessels, and I do talk about that in the book, but today I'm going to be concentrated on the close packed structures. So what are the distinguishing characteristics of the FCC structure and the HCP structure? Then what is known as close packed, and that means that the atoms are arranged in such a way that the metallic bond lengths are a minimum, shortest possible bond lengths, and to have and also the smallest volume occupied by a certain number of atoms. So because of that, the atoms are arranged typically in a hexagonal pattern as shown here. Now, once I've created the first layer, I'm talking about crystalline structures, so we're talking about basically a three-dimensional structure. So we'll start off with the first layer here, and we'll call that an A layer. And the next layer of atoms can be placed either there, which would mean the next atom is here and there, or they can be placed there. So this is what's known as if this is called this an A site, this is what's known as a B site. And if we define that as the B site, this automatically becomes a C site, because the next layer would have to be or can be stacked at that point. So to illustrate that, let's look at the second layer. So we'll put the second layer on. And I guess the light here is kind of odd, but I'm now occupying a B site, but I could equally have made this what's called the B site. So we have two options for the stacking. For the second layer, it's either here or here rotated. But then the next layer of atoms has to can occupy either an A site or a B site. Now, what do I mean by that? Let's look at a layer of atoms. We'll call that the A atoms. When I put the next layer of atoms on top in a close packed structure, I can put them on in certain positions, which then define what's called the B layer, the next layer up. Now, it just whatever fits in those. The two options we have is that or that. So let's pick that one. And once we have that second layer, the third layer of atoms can be placed on what's called the C site, which is the next available row. And the difference between the third layer of atoms is that if you look here, you cannot see through the lattice. But if I place those atoms directly above the A site, then you can see through the lattice that we have these holes, which is where the C sites would be. So this is now ABA stacking. If I put it down here, this is ABA stacking, and this is ABC stacking. So the difference is simply one, that the third layer of atoms is in this position, ABA, where this atom is directly above the first layer, this atom is directly above that, or not, in which case it is in the next available low energy site, but these three atoms are not directly above one another. So it's called a C site. So this is hexagonal close, this is face-centered cubic, FCC, and that one is hexagonal close packed, HCP. So the plane here for a HCP structure, let's start from the FCC structure. This plane and this plane are what's known as close packed planes. They're the 111 planes, and this plane here is the 100 plane. And when we shear to create the ABA stacking, this plane now is a 100 O plane, which is a prism 1 plane. You'll hear about this if you read the book. And this plane here is now a 100/1 plane. I can probably better illustrate the whole structure with a bigger model, and this is it. Okay, excuse me. I've created a ball model here, and this is a close packed plane of an FCC structure, and this is also the next close packed plane of that FCC structure. Now this is ABC stacking. So if I wanted to create a hexagonal material going from the face-centered cubic to hexagonal material, what that means is that starting at the base layer, if I shear every second plane so that by what's called a partial, a Shockley partial, if I shear every second plane, I can create a hexagonal close packed structure. So I'm going to shear them in that direction, and then this in that direction, and then this in that direction. And what I've created here is a 100/1 O plane, which is a corrugated, what's known as a corrugated prism 1 plane. And this is what's called a Martensitic transformation. So what I've done is, starting with a basal plane, which is also a twinning plane in FCC, starting with the close pack plane, I should say, the 111 plane, I can create a hexagonal close packed structure. Now, likewise, I can go from the hexagonal close packed structure, where this is now my basal plane. I can reverse the transformation and create a face-centered cubic structure, FCC structure, by shearing every second plane by the allowed partial. In so doing, I recreate my close packed 111 plane, and there's another 111 plane here, which would have been the basal plane, or was the basal plane in the HCP structure. And this illustrates to some extent why in the HCP structure, or I should mention that in the HCP structure, one cannot twin on the basal plane, or even though it's a close-packed plane, but you can create a martensitic shear. So do that, that, and that. The material can shear martensitically to create a different crystal structure.